This is Official Nerd Business.
Hello nerd boys and girls, and welcome back to our programming series. Today we are using Python 3 to take a crack at Euler problem number 21. Problem 21, as you can see, I've already created the template file I always make for these kind of problems, and it's called Amicable Numbers. Let dn be defined, so let's have a function over n be defined as the sum of the proper divisors of a number. All the numbers less than n which divide evenly into n. If this sum of divisors of a is b, and if we take the divisors of b, sum it and get back to a, where a and b are not the same, then a and b are amicable pair, and each of a and b are called amicable numbers. And here's an example using 220. Its divisors are this lot. Note, we are talking about proper divisors, and there's two ways of looking at divisors. One does include the 220 at the end here, and the other one does not. We are looking at the proper divisors being the set of numbers including 1, but not including n itself. So running this divisor sum function d over our divisors gives us 284, and if we check the divisors of 284 and sum the whole lot up, we get 220 again. So as you can see, 220 and 284 are friends of each other because they share this property. They point at each other through their divisors. Evaluate the sum of all the amicable numbers under 10,000. So note, there's a special case here. There are numbers for which the sum of divisors equals itself, so you would get an equal a and b. Those are excluded using by this bit in the challenge. Alright, so I've already set up some groundwork. I've got a main function here that doesn't call the run yet, but calls the divisors function. Run should run attempt number 1. And here is the divisor function, and it takes in n. It has a switch that can toggle between the proper divisors or all divisors, so whether or not the n is actually put on the list. We'll go through what this does in a second, and here is the bit that removes n if we've so specified, or if we haven't specified anything, it takes that value as default. So in this file I've got a call to the divisors function, and if we put in 16, we can see that we get the list of divisors 1, 2, 4 and 8. So 1 divides 16 16 times, 2 divides 16 8 times, 4 divides 16 4 times, and 8 divides 16. There are no numbers greater than 8 that divide into 16 except 16 itself. So if we were to specify that we don't want to exclude 16 from this list, there it is. So that gives us all of the divisors. It should be fairly easy. Let's see, for example, if we were to look at 6. This is an interesting number, because the proper divisors of 6 are 1, 2 and 3, and if you sum these you get 6 again. So if we take a look at the problem statement again, that would be that would not be an amicable number because it's pointing to itself. And this is called a perfect number, by the way. And that's a whole different can of worms. Let's see. So let's say we do want to call the run method instead of the divisor method. We've tested the divisor method a little bit and it seems to check out. So here, attempt number 1. We take all the numbers up to n. So there's a test case up to we can go all the way up to 10,000. It isn't particularly heavy on the calculus. Let's see if we want to store all amicable numbers. And we're simply going to check all numbers. Now we have our A's. We get a B out of these A's by checking this. And now the question is, if we take the divisors of this again, if A is not equal to B and A is equal to C, this bit excludes the perfect numbers. So if we are at iteration 6 in this loop, then this should be 6, and once we start cracking 6 again, we would get 6 back. So that's excluded by this bit. And if we take the example of 220 into 84, and then this would be 220, this would result in 284, and this again would be 220. So here's our entire logic loop. We are going to sum it in a second. I just want to have a test run. Oh dear. Looks like I broke something. For what number? Let's get into a little bit of debugging. Let's simply print out whatever n we receive and see where this crashes. Probably very early on, yes. This is a bit odd though. I'm a bit puzzled about why 1 isn't on the list. Alright, that's why. If whatever number we are going to check is less than 1, simply return an empty list. Alright, so what's going on here? The first bit was going alright. I'm going to remove the print statements again. This part was working fine, and we got a 1 was added to the list and removed again because we've so specified that n itself should not be on the list. This gave us an empty list, and when the empty list is summed it yields 0. Then we were checking the divisors of 0, which doesn't have any divisors obviously, and then we try to remove something from a list that doesn't have anything. So there was our error. If we've all corrected everything correctly, no pun intended, then this should work as expected. So here are all our amicable numbers. and here are the two numbers from the test case. Let's see what happens if we don't return amicable but return the sum of all amicable numbers. And run it through main, because I am kind of interested in timing information here. Run main 21. Default parameter of 10,000, yes. Let's see, it took us 6.2 seconds to find 31,626, and I can tell you, if you enter this over a project order, you will get the green check. So although we did get the correct answer, I feel 6.2 seconds is a bit slow. So where does this why does this take so long time to process? That's not on the attempt number 1 function here, because we could optimize this a little bit. If we've checked the divisors of A and found B and checked the divisors for B, now we only append A, but we know that B is also an amicable number, so we could include B on the list here and have it excluded from future testing. That would optimize a little bit, but not that much, because the number of amicable numbers we find also is very small. It's like 8 numbers, so 8 tests that we prevent. And we could also delete numbers that we found not to be amicable, though that would probably cause more overhead than it would solve processing wise. But there is the divisor function. So if we were to make a copy of the divisor function and edit this a little bit, we now have a very naive way of testing if a number is divisible by another number, and we've seen this problem before. It was when we were looking for primes. I've previously did a video on Euler problem number 3, where in one video I solved the problem itself programmatically, but in the other video I talk a little bit about how we can look for primes and what why the square root of a given number is involved. So we could have this loop run not up to n itself, but up to the square root of n. And to do so we need to import, math. Import statements are usually at the top of your file, but you can place them anywhere you like. I cannot place them at the top of this file, because then the this file is read again by the main py, and if there's something at the absolute top, then this isn't considered to be a docstring anymore. We can't process the docstring for all the values that we've put in, like title and parameters and description, etc. This should be alright. Let's see, I can move this import statement up closer to the top, that would be better. Then let's have a look at this. Should not go from 1 up to n plus 1, but it should go up to math dot square root of n, and the for loop doesn't like this to be, doesn't like it when this isn't an integer, so let's explicitly cast it to integer and add 1 for edge cases. And because we stop looking at numbers bigger than the square root of n, we are not going to find, if we, for example, take 16 as an example, we previously saw the list of numbers, list of divisors of 16 that included 8. But we also know that the square root of 16 is 4, so in this case we wouldn't find 8 because we've quit early. But we can do something about it, because 16 is 8 times 2, and we've already got the 2. So when we find 2, we also want to the number that we get by dividing. Let's make this an integer divide, because we know it's going to be integers and now all the data types are still in. So for every divisor we find, we add 2 numbers to our list of divisors, namely whatever number we find and whatever number, how many times it goes into. And because we know that when we move up, we will also find that number and get back at the lower one. We know that if we are looking at the divisors of 16 and we find a 2, that there should also be an 8. This is basically what this code now does. And this means that we can stop looking at numbers at 4. So this might lead to a new problem. This will in fact lead to a new problem. Let's test it not like this, but let's test it by printing the divisors of 16 again. This will do something very funny. Well, not particularly funny, in fact. Not divisors, but divisors 2, please. As you can now see, this has 1 and not 16 because we've excluded that. This has 2 and immediately followed by 8 because 2 and 8 are a couple. They are appended to this list in these 2 operations, consecutive operations. And then there's this. Now we have 2 4s. That's because 4 divides 16 cleanly, and then 4 is added and n divided, so 16 divided by 4 is added as well. Now we could put in an if here that checks if those are equal and then remove 1. We can also turn this into a set. And a set is one of the default types of collections that you can have. There's list, we use list extensively. We've seen the dictionary used. Set is another one of these. And what makes set so special, tuple by the way is another one. Set is special because every element in a set can appear only once. So when you have a list like this with multiple occurrences of the same number, then one of those occurrences is kept and the rest are dropped from the list. So by converting R to a set, we guarantee that every divisor will be named only once in this list. So if we test this again, we see that the duplicate 4 is removed and this list once again checks out. And I'm not entirely sure why it moved 8 all the way up to the front, but we are not concerned with the order of the digits here. We are, or of the divisors. We only want the numbers themselves. So if we would say that attempt number 1 doesn't use the divisor function, it uses divisors 2. Let's see if this speeds things up. Let's once again hit main.py. Problem number 21. That was a lot faster. That's it for problem 21. There is an overview for this problem on the Euler website. That yields a lot more information, even more information. There's a third way in which you can do this. So see if you can, if you check out the document, see if you can implement solution number 3. I will leave you with a link to my GitHub where all my source code can be found in the description box below, and I will see you next time for problem 22. Thanks for watching this video on Official Nerd Business. Don't forget to like and subscribe and click the bell icon. Did we discuss everything you wanted to hear, or did we miss anything? Any topics you want to hear in O&B? Leave your thoughts in the comments. See you next time.